So today we're going to do n-body problem. So after this should be everything that you need to do the homework. Originally it was due next Monday, like 1 week from today. I'll probably extend it to next Friday. Yeah, but I'll put there's only one homework after this one, so I'll put that one out at the regular schedule, but I'll just extend this one. Yeah, are people okay? Like, so PA3 is ongoing. Have people tried it? Are you able to run it? Any issues? Good. So that should be due in a couple of weeks. So today we're doing hierarchical methods for the n-body problem, which is another one of these classic famous algorithms in HPC. So the main motivation for these algorithms is simulation of particles, or they call them bodies, but basically it's a simulation of particles, or it could be like celestial bodies, like galaxies or planets, and the interactions that they have on each other. And so computational simulation is one way that people try to make discoveries about these kinds of bodies, because it's hard to gather data about them, because they're large and maybe on the scale of like planets or galaxies. So computational simulation is one important way that we can try to learn about those things. And often these simulations can be pretty big, possibly on the order of several million variables, like planets or bodies, stars, or even more. And most problems boil down to solving matrix vector products. It's kind of something that we have in FFT also. You could solve it in matrix vector product, but people come up with clever algorithms to try to do it in a better way. And normally, doing matrix vector product would take n squared time, because the matrix is n by n, and you have a vector of size n, and so doing this interaction could boil down to doing just this product. And similar to the FFT, we want to bring this, we want to do some kind of smarter algorithm that drops down the time to n log n. So one of the original algorithms for the problem takes time n log n, and the more famous one, the fast multiple method, takes time order n. And the high-level idea about all these, so these are all, dropping these times down to n log n, or order n, are all based on approximation algorithms, because the high-level idea is that you don't need, so basically what we're trying to compute is that we have, you can think of it as like a planet. So you have some planet, and you want to compute some force from all other planets onto this planet, and you want to do it for all the planets. So if you have n planets, it's going to take n squared time. Each one takes n to compute the forces of everyone else onto you. And the main idea is that you don't actually need to compute this exactly. So to compute it exactly, it's called direct methods, but the high-level idea is that we can use some sort of good approximation to try to get us close to it, and to drop down the time, either to n log n or to order n. And the idea is that we want to compress the dependence on distant data, which means that, so if you think of these as planets, some of them are close to you, and some of them are far away for each planet. And the idea is that you can approximate the faraway ones using some sort of approximation, like basically averaging out the forces from all those other planets that are far away for some definition of far. And then you do some exact computation for what's close to you, and you have some sort of coarse-grained approximation for things far away from you. And the idea is that that is close enough to get some idea of what the interaction is without having to do a high level of computation. And compressing this data by groups of points, which are far away, can reduce the work and the communication. So first it reduces the work because you don't have to do every single other interaction onto you. You just have to look at the average and do that interaction onto you. So that reduces the work, and also reduces the communication, because if that thing was far away in a different processor, you would only have to transfer one piece of data rather than however many pieces of data correspond to the points on the other processor. And so some examples where this is used, elliptic PDEs in graph partitioning, and the one that we're going to focus on today is Barnes-Hut or fast multiple method for force interaction, like electrostatics or gravity forces. So this is some high-level pseudocode of the type of simulations that people run for these things. So you have some time, t, And while t is less than some t final, so you want to run this interaction for some number of time steps, you have n points, for I is 1 up to n, you compute some force, which is the force on particle I. And once you compute that force, you move the particle under force f of I for some time dt, which is related to the time step. So you compute some force on you, and maybe you want to compute some interaction, like movement due to gravity. And then, in addition, you may compute some other properties. The time moves forward by dt, and that's the end of the while loop. So that's a very high-level view of the simulation that needs to happen. And normally, with direct methods, this line, compute force f of I, which is the force on particle I, would take order n time for every point. Because the naive way to do this, f of I is you sum up over all particles that are not you, the force on you from k, where k is some other body. And so the obvious algorithm for doing this computes, like I said, this n squared interaction, but we want to drop this down to something much better than that, because if n is in the millions, n squared is intractable. Is the problem clear? So yeah, and it turns out that particle simulation is one of these big problems in HPC. People are still working on it. Yeah, so in this IEEE magazine that I mentioned last time, they labeled the top 10 algorithms of the 20th century, and the fast multiple method is one of them again. And n-body simulations are frequently used in scientific computing. And for a long time, I would say the first ones came out in like the 70s or so, and they were really popular back then, and people are still doing them. But we have a lot of nice methods for them already, so people are not actively working on them so much, but it was because they worked on it for a long time back then. So last time we had FFT, and here's n-body simulation. And red means that it's most heavily used in HPC. So some applications of n-body simulations, like I said, like in astrophysics and celestial mechanics. So when trying to measure how astrological bodies interact with each other, one way to do it is through these n-body simulations. And in 92, this paper, so it was a long time ago, but in 92, they did it on 17 million particles for 600 time steps in 24 hours. And back then, this is kind of amazing because back then they didn't have as good computers as we have now. So this won this Gordon Bell Prize at supercomputing, which every year is awarded to is the highest honor in high-performance computing for solving big problems. And back then, they did it at 5.2 gigaflops, which today maybe doesn't feel like a lot, but back then, because they didn't have such high clock speeds, it was actually a lot. And they could do 44K flops per particle per time step. And they had 1% accuracy. And just as a back of the envelope calculation, if they did the direct method, which again is this n squared computation, at this same gigaflops, it would take them 18 years. So they did it in 1 day, but without approximation, it would have taken much longer. So that's one example of why it's good to do this sort of approximation. And they did it with pretty good accuracy, like 1% is not a huge loss. Another example more recently, even 2009, they were doing this turbulence simulation. And in 2009, they had GPUs, so they're doing it on an older generation of GPUs back then. They did it on almost 17 million particles, about 16.8. And that won the Gordon Bell Prize in 2009. And they did 20 teraflops. So in 92, they had 5.2 gigaflops, scaling up by orders of magnitude to teraflops. And now we can do even higher than that. It's just an example of what orders of magnitude we're looking at to do the simulation. So like I said earlier, the very high-level idea is that you want to compute some force on every point from all the other points. And the way that we drop down the runtime is to approximate the force from ones that are far away from a spatial perspective. And then we do some exact computations on the ones that are close by in quotation marks. And we'll see what that means later. later. And all of these rely on the same idea, which is, so just given this example, consider computing some force on the Earth from all celestial bodies. And we can see some number of stars in the sky. But however, if you look at one star in the sky that actually corresponds to some other galaxy, and inside that other galaxy, there are many other stars or bodies that compute some interaction on the Earth. And so that is going to take a lot of time to do this exact computation. And the idea is that we want to compute all stars in some faraway point, like another galaxy, by a single point that approximates all the bodies in that other point, which is the center of mass and the total mass. So the total mass is just you add up all the forces in some faraway box, and center of mass is some weighted average of those points. And so with that approximation is done in some pre-processing step to compute the center of mass and total mass. And once we compute that, then in the further interaction computation, we just use that approximation on every point. So that's called far field approximation, which is you use this far away approximation to compute the force onto you. And the way that we decide what is far away and what is close is determined by some distance, which is the size of the bounding box, and r, which is the distance from that center of mass to the Earth, which is the particle that we're trying to compute the force interaction on at this time. And so d and r are both parameters of the simulation, and there's some parameter that is given relative to d over r, and if d over r is below that parameter, then it's considered close, and if it's above that parameter, it's considered close, because as r goes up, this thing goes down. So below that threshold means that it's far, and above the threshold means that it's close, and if it's small enough, then it's far, and you use this approximation. And this idea is not new to this force computation. Newton used it by approximating the Earth and Apple using the center of mass. So the new part is that, so this is one idea, to use the galaxy as a large bounding box and try to take the average within it. And the high-level idea in all these algorithms is to use this approximation recursively. So that part is maybe a little bit hard to grasp, which is within one galaxy, there's two issues. One is that you're trying to compute the force interaction for every point. So from Earth, we're trying to compute everybody's interaction from everybody else onto Earth, but we're also computing the interaction of Earth onto everyone else, which makes this is why it's computationally hard. And yeah, so one way that we're going to deal with that is within these bounding boxes that are far away, we also want to compute the interaction of the bodies in another galaxy, for example, onto all points in the galaxy. And so we use the idea recursively. And so within the same galaxy, there's some things that are also far away, even with respect to those points. So that's this recursive idea. And then the idea of the recursion is that you compute the center of mass and the total mass for recursively smaller bounding boxes. Questions so far? Come back a little bit. Yes.
Wait, so sorry, just to clarify, we're using the structure recursively, and it's basically the structure is like the Earth is way of calculating the bounding box of like the Earth on all other bounding boxes.
Yes. So somehow we need to divide up. So we have you can think of it as a 2D grid in space. The simplest version is a 2D grid in space, and you have some points in the grid. And for every point in the grid, you want to compute the force of all other points onto you. Yeah, so basically what is going to happen next is that we're going to decompose this grid into bounding boxes, and then some of them will be far and some of them will be close, depending on which boxes are neighbors to each other. Does that make sense? Yes.
So we already
point. So maybe I will clarify further on, but the idea of the recursion is that in the first level of the recursion, you have some boxes that are far away and some boxes that are close. And then when you further cut down the recursion, within the next level, there are some that are far away and some that are close, that were close in one level above. And so the idea is that you recurse to some level down, and you keep doing these far field approximations until the leaf level. Any questions? So the basic data structure that we're going to use for these n-body simulations is called quadtrees and octrees. And so these are something more fundamental. Like you could use quadtrees and octrees for other applications, not just n-body simulation. They're frequently used in like graphics processing, for example. Quadtrees and octrees are like these classical spatial data structures. And the idea is that you have some, in the simplest case, a 2D plane. And we have some points in the 2D plane, and we want to represent their spatial distance to each other using this tree formulation. And basically what's going to happen is that if this is the 2D grid, we just recursively cut it into quadrants. So that's where the quad comes from. At the highest level, the blue line is this first cut at one level of the tree, so that's these blue points. And then at the next level, each node here corresponds, so each quadrant here corresponds to one of these. And then you cut it again recursively into quadrants, and that's these 4 red points here. And then again, these light blue get cut here into those. And with points, yeah, and then the quadtree, initially it just contains the points. And you can imagine when you build this tree, in the point case, all of the points are stored at the leaves because they're just points, and so they're neatly contained in the bounding box if you cut the ties in some way. And then we can compute some metadata on it. Like earlier I was talking about the center of mass and the total mass. And the center of mass and total mass are determined by the bounding boxes. Like, for example, in this small light blue box, the center of mass, we would compute it by taking the weighted average of all the points in this light blue box, which is the leaf. And then one level above that, in this red box, the center of mass and the total mass can be computed from the values in the light blue boxes. So you can compute them recursively going up. So yeah, so the first step in all these simulations is to build the quad tree and possibly do some pre-processing to compute the center of mass and the total mass. And it might also, so in the beginning it contains like the coordinates and some weights. You can do the pre-processing, and there's this notion that in this complete quad tree, every node has 4 children, besides the leaves. And that is true if the points are vaguely uniformly distributed.
So we're not calculating the actual center mass given the points inside the box, we're just using the box itself.
Could you say it again?
Are we calculating the center mass from the points inside the box, or are we calculating the center mass past like the box itself?
Good point. So the question was like, are we covering the center of mass from the points or just the bounding box itself? So at the least, we have to do it from the points because there's no lower information to use. So at the least, you actually just directly compute the center of mass and the total mass. At the higher levels, this is like an optimization. At the higher levels, you can just aggregate the lower level information to compute the center of mass and total mass for the higher points, or for the higher nodes.
So you said that it's uniformly distributed in this box.
Yeah, so in the beginning, let's just assume that the points are uniformly distributed in the 2D grid, which makes it easier because then we can assume that the quad tree is complete. Yeah. So that is quad trees. And so that thing where you compute it from the bottom up is an optimization. The most naive way is, of course, like you start from the top, you compute over all of the things. That you can, of course, you can iterate through every point and compute the whole center of mass and total mass at the root. And then you can do that here, do it in this entire subtree, and so on. But the optimization that you start at the leaves and you use the information as you go up. So maybe we can get into this a little bit later. So one major step in the forced interaction computation is to pre-compute the center of mass and the total mass. And maybe the most straightforward way to do it is like you start from the root. You notice that all the points are corresponding to this root node, and then you compute the center of mass and total mass over all the points. And now you need to compute it for all the internal nodes. And so if you compute it at this internal node, then you look at all the leaves underneath it, and those have some points, and then you compute it for this node. And you can do that for every internal node. And that would be correct. The more optimized way to do it is you have all the points of the leaves. And for every leaf, it has some number of points in it, and you can compute the center of mass and total mass for those points just directly. And then you can notice that the internal nodes, like the parent of those 4 leaves, the center of mass and total mass depends only on the aggregate information that you've computed in each leaf. And so more optimized would be you compute it at all the leaves first and then go up. Other questions on this one? So this is important because this is the data structure that we're going to use for all these interaction computations. And then octrees are just the same but in 3D. So rather than 4 quadrants in 2D, you cut 8 octaves, 8 subparts in 3D. And so it's the same, just everybody has 8 children rather than 4. So how are we going to use this? All of these approximations for n-body simulation begin by constructing the quadtree to hold all the particles. And if they're particles or points, they can all be stored in the leaves. And each node corresponds to some spatial bounding box in the grid. So the root corresponds to the entire grid. The one level below the root corresponds to the quadrants from the whole grid. And then one level below that is 1/16, and so on. And you basically keep going until there's some pre-specified level, or until there's some constant number of particles in the leaf. And so it's easiest to think about if the particles are uniformly distributed, because then there are an even number of particles per leaf. But in most cases, the particles are non-uniformly distributed. And so if you build the complete tree, most of the nodes would be empty, which would be a waste. So there's some notion of adaptive quadtree or octree, where you only store the nodes that are actually there, and you don't need to keep storing entire subtrees if there's nothing further. But the high-level idea is the same, of like cutting the spatial bounding box, but it's just whether in the representation you keep actually storing the pointers or the nodes further down if there's nothing there. This is just an example of an adaptive quadtree. So this is the grid, the whole 2D grid, and at the first level you cut it here into 4 pieces. And it just happens that these two each have one single particle in them. So we don't need to keep further dividing. We could keep further dividing these 4 by 4, and then one of the leaves would have 1 particle, and all the rest of the leaves under the subtree would have nothing. And so, realizing that case, we just cut off the tree here. And so on similarly in the other paths. So in the other ones, there is more stuff, but still in some quadrants, there's only one level down here. These 3 only have 1 or 0 points, and so there's no point to further divide the subtree. And then in practice, when you actually build these things, you set some parameter that's the minimum number of particles you need to keep recursing. So in each step of, so if you remember earlier, closer to the beginning, we were saying you run the simulation for some number of time steps. And the easiest way to do it is at each iteration of the time step, you rebuild the quadtree or the octree. Because so you build the quadtree, you compute the forces, and things may move due to the force. So things may have moved, which node they are in the quadtree. And so the simplest way is to rebuild the quadtree, because it turns out that rebuilding the quadtree is actually small in time compared to do the simulation. So yeah, so the cost of building this quadtree is proportional to n, the number of points, times the maximum depth of the quadtree, so the height of the quadtree. And if it's uniform, then the depth of the quadtree is proportional to log n, like log base 4, but that's order log. So the cost to build it is n log n. And if you have an arbitrary distribution of particles, so potentially non-uniform, the depth could be proportional to how many bits you have in the particle coordinates. And then if that is parameterized by b, then the cost to build it is proportional to b times n, where b is the maximum height of the tree. Yes.
So, with the time changing, the quadtree structure will change, right?
Yes. So in every time step, you may rebuild the quadtree.
Yeah, so, how we make sure that to follow the hierarchical communication?
Oh, that's a good question. So I totally didn't cover how to build the quadtree. So I said that you can do it. So this time is just like in sequential time. If you just have one processor, you have endpoints, how long it really takes you to build the quadtree. Doing it efficiently in parallel is a different but interesting point that is a little bit in the homework. So, it's not like you don't have to do it from scratch in the homework, but you'll see it if you read it, which is like, so you have the spatial grid. And ideally, when you build a quadtree, you would like to have things that are spatially close to each other in the sorted order. But in normal sorted order, like if you just sorted by x or y points, or sorry, x or y coordinate, it's not necessarily true that things that are near each other in the sorted order are close in the 1D sorted list. And so there are different orderings that you can sort on that move them closer together. If we have time, I can talk about it. Because it is interesting, but for now we can finish the simulation part and then come back to it. Other questions? So this n log n comes from sort of like a naive, so in just one thread, forget parallelism for 1 second, you have endpoints, and basically what is trying to happen is that you're trying to partition them into quadrants, or whatever buckets there are at that level, and it will take order n time at each level to partition them, because you know where the bounding boxes are, that's just fixed based on the level, and so you just can mark where they are, and then move them together and go down one level. So in an unoptimized ordering, or in an unoptimized algorithm, you can still achieve something like that log n. So that is quadtrees, and we're going to use them to understand this Barnes-Hunt algorithm, which is an n log n approximation for n-body simulation. So Barnes-Hunt is one of the first approximation algorithms for n-body simulation, and it has these 3 high-level steps. Let's just do it in 2D, because it's easier to understand. So the first step is to build the quadtree. You have some endpoints, and you build the quadtree just as we talked about. And and that takes time n log n, or b times n if it's non-uniform. And then the second step is for every node in the quadtree, this preprocessing step is going to compute the center of mass and total mass for every node. And we already talked about it a little bit, but you can bound it above by n log n. Even doing it top down will take you n log n. Doing it bottom up will take you order n. So either way, you can bound above by n log n. And then, so this part we talked about a lot already, but the last part is the new thing, which is that for each particle, then we use this preprocessing to compute the force on it using the faraway approximations of center mass and total mass. And the exact constant depends on the accuracy, but it's bounded above by n log n. So this is step 3. So we have nodes in the quadtree which correspond to bounding boxes in space. And basically what is happening is that for every bounding box at some level, we consider all bounding boxes, all other bounding boxes, all other particles in different bounding boxes as far away. And so we use the approximation to compute on the points in this box. And yeah, the goal is to minimize the number of nodes that we want to, that we need to compute the force, subject to some accuracy constraint, where the accuracy constraint is dependent on the side length of the node and the distance from the given particle to the center of mass of the other node. And then this theta parameter is a given to the simulation, and if d over r is less than theta, then you use the approximation. Otherwise, you use this near field approximation of doing exact computation. And so as r goes up, which is the distance from our particle to the center of mass of a different bounding box, as r goes up, this d over r goes down. You can see an example, so that will probably help. So suppose that we're trying to compute the force on this particle. And so this is somewhere in the quadtree. This is just the quadtree. And say that this particle is in this node of the quadtree. And so all other nodes at this level are considered far. And so we use this approximation. Well, this yellow box just means that we're going to use the approximation rather than the exact computation. So here, this node, or this box, corresponds to this node. This 3, which is how many points. And then these other boxes, we have pre-computed the center of mass. And so we just use the center of mass to approximate the force on this point. But there are some other points in here that we didn't consider yet. So that's where the recursive part comes in. So we go down one level of this recursion into this node. And now these are the 4 subquadrants in here. So this 1 is this quadrant, and this 3 is this one. And so we're going to try to use as much as we can as the far field approximation, even recursively within this quadrant. So we go down 1 here. This red point that we're considering is up here, and this bounding box down here is far according to the theta parameter that we just described. And so again, recursively, this yellow box means that we use the center of mass approximation up to the given particle. And this green point is close according to d over r, and so we just use the direct computation of green onto red. But for every other point, it's captured by the approximation. And this is going to happen for every point in the entire simulation. So this example was just 1. We computed the force of everyone onto here, but like we're going to repeat it for every other point in the simulation. Yeah, and the point is that in total there are 24 points. So normally we would have to do, without approximation, we would have to do 24 calculations of something else onto this particle. But in this example, we only have to do 5. There's 1, 2, 3, 4 approximate calculations and 1 direct calculation. So that's how we can cut down the work significantly. So you might notice that so far, like, we haven't talked much about parallelism, besides the question earlier, and that's because the first step to making an efficient parallel algorithm is making an efficient sequential algorithm, because if your sequential algorithm is poor, then parallelism cannot save you. And so we're going to focus on the sequential case first. All these optimizations are just sequential, like they just have to do with the approximation. This one? Oh, I see. Why can you not directly use that? Because the center of mass here would, there's no numbers exactly shown, but the center of mass in this thing would be within D, or would be D over R is above theta for this thing. So like the whole center of mass of this quadrant is too close to be considered far. So earlier we had this thing, D over R. D is the side length of the node, and R is the distance from the current particle to the center of mass of the bounding box. And so in this example, the center of mass here of this box is too close to this one to use the approximation, but when it recurs down, this center of mass is far enough. Question? Yeah, so that, I think that is probably the most challenging part of this, is that this whole thing is it's recursive in the bounding boxes. And so even if this whole box is too close, it may be that some boxes in it are far. What happens if it crosses the boundary? So it may, like, in the next time step, so just as an example, like let's say this one moved here. When you rebuild the quadtree, this would be represented here instead. And then you have to recompute, in every iteration, you have to recompute the center of mass and total masses, because particles may move, and so the center of mass in each bounding box may change. This is just an example. Oh, sorry.
So what if 2 points are getting very close to each other? So we need to split a lot of blocks to separate these 2 points to a different box.
Oh, I see. Like here, you mean? So in practice, when you build the quadtree, you set some parameter about the maximum number of particles in the leaves, and that's where you stop building. And that parameter is probably greater than 1, maybe some 10 or 100 or something. So if they're very close, you won't have to like divide infinitely. You'll just be in the same leaf. Okay, so this is just some example performance analysis. The x-axis is running time, down is good, and the y-axis is running time. The x-axis is number of points. So we expect the time to grow higher when you have more points, because all the times depend on n, whether n squared or n log n. And so this is the direct computation, the naive version, and we expect that the time is the highest. And the higher that theta is, the faster it will go, because that's a looser approximation. So if you remember, theta means if something is the d over r, if it's below theta, then it's too close. Yes. Yeah, if it's below theta, then it's close. It's above. Wait, no, other way around. it's above, then it's far. It's lower, then it's close. And so higher theta means a looser approximation. And so we can see that the time decreases with theta. And then on the other side, there's error. Y-axis is error, down is good. X-axis is number of points. And you can parameterize these by theta as well. So theta 1.5 has higher error than theta 1 and theta 0.5. And here the average error is determined by the average vector distance, because we're computing. If you remember, like from the beginning, this is really like matrix vector product. And it's just computed relative to the exact computation. And these are all, this is a very small example, like only 10,000 points, but here less than 5%. So in practice, here theta equals 1 is pretty good. Questions?
So for the first, the 1996 example you showed earlier, at a 1% accuracy, so this is, I guess, acceptable, but good. How do you check that accuracy? How do you consider it take some amount of years to do it?
That's a good question. They probably didn't run the exact computation for the entire thing. I don't know, let me check that. It's a good point, actually, yeah. Maybe they did like a smaller test case and then just called it 1% accuracy. That's my guess, but I'll look into it. Any questions? So yeah, we're gonna move on. So that was Barnes type, and next we're gonna do fast multiple method, which is an order n approximation for that body problem, where order n hides some constants, but you can indeed that it is, you can prove that it is actually linear. And it uses a lot of the same ideas from Barnes type actually. So there's just some small tricks in here that make it theoretically asymptotically lower. So one of these famous algorithms from HPC, the original paper was in '87, and since then has won many awards. And so it has several main differences from Barnes-Hunt simulation. The first is, so in Barnes-Hunt you directly compute the force approximation, whether through center of mass and total mass approximation or through direct computation with those close to you. In FMM, it computes the potential at every point rather than just directly the force. And as a result, FMM uses more information in every box rather than the center of mass and total mass, which are just one single scalar value for each of them. Instead, FMM uses an expansion of some sort of approximation, and in the expansion has a bunch of different terms. And the accuracy of the FMM and the runtime depends on how many terms you expand this boolean. And then, as a result, because it computes this potential, the way that it gets down to order n is that it computes a fixed set of boxes at every level. So it doesn't use this d over r parameter anymore. The number of boxes computed at every level is fixed based on the neighborhood information in the quadtree. And yeah, so Barnes-Hunt uses fixed amount of information in every box, but the number of boxes changes with the accuracy parameter. And in contrast, the FMM always uses the same number of boxes, but the information per box that you compute on with the expansion changes depending on the accuracy parameter. And we'll just see more information about this. Like, this is a bit abstract right now, but we'll see some examples and hopefully it becomes clear. Yeah. And so the two expansions in FMM, the outer expansion is ones that are far away, and inner expansions is one that are close by. And we want to compute, so the high level goal is the same. We want to compute the force from every point, or yeah, from every point onto every other point. But this is just a different approximation way. So suppose we have some points, x sub I for 1 equals to I equals 1 up to n, and some charges for f of I equals 1 up to n. And we have some approximation function. So here g of x and y, g of x and y. In 2D, it's natural log of x minus 1. In 3D, it's 1 over x minus y. And basically what we're trying to compute is the potentials, which are represented by u sub I, for I 1 up to n. And you sum them up, which is this function, x of I, x of j, and force of x of j. So this is some interaction from j onto I, and you sum it up over all j. And you can express this with matrix vector product, because the number of entries, the number of possible pairs of I and j is n squared, because you have n points. And f of j, there's one for every point, so you can think of it as a vector. And so you would be able to compute this vector of u of i's directly with matrix vector product. But again, matrix vector product is n squared, and we want to do better than that. Yeah, so direct computation is order n steps, which is too expensive. We want to lower the complexity. And the main parameter, the accuracy parameter in the FMM is epsilon, which shows up in the constant in this order n. But basically the epsilon corresponds to the number of terms that this thing gets expanded. And their form, so this, like these functions, it's, for our purposes, we're not going to consider where they came from. It's just the high level idea is that, like in the original bar set, it just depends on the force from the other points. Here we also have this expansion, just a different means of approximation, and the idea is that you can expand out terms on functions. But the actual high level flow of the computation does not depend on which terms we're going to use. So we're just going to not think too hard about this for a second, but just consider the very high level flow of the approximation. So the first idea is similar to the bar set simulation in that you have bounding boxes and you have points in bounding boxes and you want to approximate them with one single point. So that idea is the same. And the idea of using these approximations for faraway boxes is also the same. So suppose we have some box B and some box A, and they're considered far away for some definition of far. And normally, to compute the interaction of every particle on B, on every particle on A, that would take n squared. But if they're far away, we do this approximation by computing the center in order n time, and then doing the computation of the center onto, you compute the center of B and A, and you approximate the interaction by computing the effect of the center of B on the center of A, and then propagating that to every point in A. So this is a very coarse-grained approximation, but it will reduce the time significantly from n squared to order n, because it takes order n to collapse all these points into this one point. It takes order n to collapse all those points into this one. It takes just order 1 to compute B onto A. So the cost of doing this 3-step approximation is if there are n sub b points in B, n sub a points in A, the time goes down to n sub a plus n sub b, because costs linear in each of them to condense down to 1 point, costs 1 to do this expansion times the force onto here. And so you can we aggregate both the force and the center. So this is similar to the bar set. And we're going to use this it's called far approximation, whenever A and B are well separated, for some definition of well separated that we will see shortly. And then you can think about it this way as well. So the normal, this matrix vector product view would be this tree x of I, x of j for all x of I in A, x of j in B. And then you have a vector of the forces in B, and you can multiply them to get the forces in A. But this, you can kind of use low ranks approximation, or instead you just make this matrix into one point. We've condensed down A and B into their centers, and we do vector multiplication. And so this will reduce with time, it's true. The main issue with this, or not issue exactly, but one main consideration is that in n-body simulation, every point is both the source and the target. So you're trying to compute the force of everybody else onto you, and the force that you are also going to contribute onto everyone else. And in Barnset, it was very clear because like the most direct way to implement it is you take every point and then you compute the bound, like who is near and far in the bounding boxes. And so it's the view of you are the center and then you're computing everybody else onto you. That's the first one, so the high-level ideas are all very similar, which is the first one is this near and far approximation. The second one is, again, this hierarchical decomposition due to bounding boxes. So this is just the same quadtree idea that we had earlier, and you just recursively partition the plane until you get order 1 points in the leaf. You can stop. We're going to use the hierarchical decomposition to determine who is near and who is far. This is similar to what we had before. Keep going until you have order 1 points in every leaf. And if you have n points to begin with, if they're uniformly distributed, there are log base 4 levels, order log base 4 levels. And the number of boxes on some given level L is 4 to the L, where you start at 0 and then you go down to log. So the number of bounding boxes at the top is 1, sorry. L is 0. 4 to the 0 is 1, and that's just the root. And one level down from there is 4, and 16 and so on. And at the end, the total number of boxes is n, because 4 raised to log base 4 of n is n. So we're going to use these bounding boxes to determine how to use this near and far approximation. And at a high level, basically who is far is in a bounding box that is not directly adjacent to your bounding box. And who is near is in a bounding box that is directly adjacent to your bounding box. And that idea is applied recursively. So things that were near at level 0 or level 1 of this quadtree may be far at level 2. So at level 0 and level 1, everybody is near, because like in level 0, there's just one box. So everybody's in the same box. And in level 1, everybody is in a neighboring box. There's only 4 boxes. And so at level 0 and level 1, we are not going to use the 3-step approximation that we just described because the boxes are not well separated. Or well separated means the box is not adjacent to you. But however, things start to happen at level 2. And suppose that we're considering the force of B onto A. And here white is near to B and gray is far with respect to B. So we're considering A. And so we can use this 3-step approximation for B onto A. And actually we can use the 3-step approximation from B onto all these light gray boxes, because those are considered well separated. They're not neighbors of B. And that idea can apply to every box in this decomposition. So every box has some that are near and some that are far. And it's just depending on who's surrounding you in this decomposition. And so here we will just consider the force of B onto every one of these points, or onto every one of these boxes. And then you would do something similar, like this box has some far boxes from it, and you would consider the force of this box onto the others. However, we didn't consider what was in the white part, and that's where the recursive decomposition comes in. So what about the interaction of B into its neighbors? We just go down one level in the decomposition. So let's consider this one level lower in the decomposition. Just look at this B prime box. All of its, so this dark gray part is things that are already done, because at the higher level of the recursion, we have already computed the influence of B onto these faraway ones. So we don't need to do it again. But now one level down, we have some new boxes that are now considered well separated, and those are in light gray. And again, white is near boxes. And so just consider, like in this example, considering the effect of B prime onto A prime, we again do the similar three-step approximation. It's now just one level lower in the recursion. And so the high level way this is going to go is at every level of the quadtree, you get some new boxes. So you consider every box, and the boxes that are at every level of the recursion, there are new boxes that are considered well separated from your current box. And the ones that are well separated can be computed using this approximation. And the way that we're going to try to prove the linear time is by making some argument about the interaction list, which is the number of new boxes that are at every level. And the interaction list is constant. It's always, at most, 36 minus 9. Because there's 9 around you, and you get 36 new ones. And then this just continues. So in level 4, we have something similar. The boxes get smaller, and now the stuff that is in dark gray is finished because it was computed at higher levels. The stuff in light gray is new faraway boxes from E double prime. And if, suppose that this tree is of height 4, if we can't go further, then we just evaluate the neighbor influence directly using the direct computation. So this is a bit different from the FMM in that we use the bounding boxes directly. Or sorry, it's different from Barnes Hut in that the FMM uses the bounding boxes directly and the neighbors of the bounding boxes directly, whereas in Barnes Hut, it's based on like this distance from the current particle to the center of mass. This D over R thing. So this is the high-level algorithm. For each box B in the tree, compute the aggregation F sub B of the sum of all the points in B of F sub J. So this is like the same thing that we were doing before, computing the center of mass and total mass in the quadtree. And then this part, 2 through 4 are new, where for every level, from 2 to the last level, and for every box in that level, for every A in that B's interaction list, you compute this three-step approximation. And we have just said that this for loop has order 1 iterations. And so the time depends on this thing, how many levels and how many boxes there are at the levels. And then, so this is aggregating some far approximation onto every box. So every box is both the source and the target. And then after computing this entire aggregation, this approximation, then for every point, so u sub I is every point, x sub I is the point at A. And then for every box A, we compute this u sub I plus u sub A, where A is the force in the whole bounding box that contains x sub I. So there will be many A's that contain x sub I as you go recursively down the tree. Basically what happens is, like, at the bigger boxes, we compute the approximation of the bigger boxes onto this big box. And go level down, we compute the approximation of the smaller boxes onto the smaller box that contain u. And the entire approximation is by summing up all those interactions. And the last step is just, once you get to the leaf level, you do the exact approximation. Or sorry, you do the exact computation. So, how do you prove this, or how do you prove the time? The most naive way to do this is top-down, as we discussed. Better to do it bottom-up. It can be bounded above by n log n. We can also do it in order n bottom-up. In step 2, so this is like the new part in the FMM. For this given level, there are 4 delta L boxes, like we said. Each one has order 1 neighbors in the interaction list. So, summing them up, assuming that you have already calculated this f sub b, it just costs order 1 once you already have f sub b. And so you sum up the number of nodes at every level, the total number of levels you get, and it's order n. So that's where, this is like the main work in the FMM, and based on these bounding boxes and its order. It's based on the number of boxes, and the number of boxes is order n. So this part is the actual part where you compute the interaction. And that's order n. This part is just, it's called upward accumulation. It's propagating. So these are the results of this approximation in u sub A, and this part is just propagating the results of u sub A for all different A's onto the individual points. And this is the exact, just considering the ones close by in the leaves. And so we have these, in the naive analysis, we have n log n and n log n for these steps. This is pre-processing f sub b, and this is post-processing u sub I. We have this step of the interaction list is order n, this step of the leaves is order n, and we want to get it down to n. Well, we already talked about it, that we can do these steps, this step in order n. And you can do a similar trick in this one. And the way to do that is, like we talked about, reuse the computation. So from the bottom-up traversal, f sub b is just the sum of all the children. If b is this bounding box, and it has b 1, 2, 3, 4 quadrants, then the total mass in b is just summing up the total mass of b1, b2, b3, b4. And if you already have these, then it takes constant time to complete them. And it takes order n time to compute f sub b and all the leaves, and then it takes order n time to pass it up the tree. You do have to traverse the quad tree bottom up for this one. You can. If you imagine writing the code, you first out to the leaves and you come back up. And then in reverse, if you have this bounding box A, which contains A1, A2, A3, A4, to pass it, to push down u sub A into A1, A2, A3, A4, just pass it down, and you add them all the way down. And that also takes order 1 time, once you have the thing at the top. So that's traversing the quad tree top down. That's bounded by the number of nodes in the quad tree, which is order n. So the same steps, we can get them all into order n, and so the whole thing is order n. With some constants. So that is part. I think that, at least for me, the part that I find hard is like the thing about the interaction list. That part is a little harder to understand than the bar set, because like in the bar set, it's directly about the particles and trying to compute the bounding boxes onto that particle. But here, it's only, the high level is mostly only about the bounding boxes and what is near and what is far. So far, there have been three main ideas in this FMM. First is this far field approximation, where if things are far, then you use this three-step approximation to compute the approximation of the entire box B onto your box A, and vice versa. So every box is B and every box is A at some point in this computation. Second step is to use the hierarchical decomposition to identify what is far and near based on the neighbors in the bounding boxes, or the neighbors of the bounding boxes, which are determined by this quadtree. Finally, is to reuse the computation to compute the total mass by either doing this bottom-up accumulation for the pre-processing step, or the top-down, push-down, once you compute the potentials U sub A for all the boxes A. Then the last piece is, we didn't talk about accuracy really. Right now, so far we've just done like this high-level flow of what is being computed and which bounding boxes are interacting with what. The last piece is about accuracy. So not just compute. So you can think about it in terms of what is interacting as just the total mass. But ideally, for better accuracy, we would like I was saying earlier, some expansions. So like the mass distribution rather than just one point of total mass. So that's the last step. And so far, for ease of understanding, F sub B is the sum of all the charges in B. U sub A is the potential of C sub A from the well-separated sources. So U sub A is some approximation of the force onto A from everything that is far away. And this has low accuracy if A and B are not far, and also has low accuracy because F sub B is a loose approximation of what is in B. And the idea of increasing the accuracy in the FMM is rather than just using one value for the sum of charges, you use a compact representation using some terms in the function for the charge of B in well-separated regions. And similarly, U sub A is also a compact representation. This part is not really related to like the high-level flow. It's just related to when you actually think about like the effect of B onto A. Is it like one addition and multiplication, or is it a multiplication and addition of functions? And that's why it gets more expensive if you want lower error. So if epsilon gets lower, then the number of terms in the expansion gets higher, and so the constant gets higher. Yeah. So rather than representing F sub B, U sub A is a single value, represent them as a series of coefficients in a function expansion rather than one single term. And the calculation of the total mass now becomes proportional to the number of terms. Let's call it P, and it's linear if P is order 1. This part is less important than like the high-level quadtree bounding boxes thing. So to summarize this part, the FMM has 4 main ideas. This low-rank interaction, so this 3-step approximation, the hierarchical decomposition, and reusing the computation. And the last one is this compact representation, based on not just one point, expansion of several terms. And so far, so there's a lot of work on the APM, like the original paper is there, but since then there have been many follow-up works, and some of them are working on if the points are not uniform, how do you make the algorithm adaptive and still get a good runtime? I think I'm out of time, but I'm happy to take questions. Okay, if there are no questions, I will leave this part for next time. It's not super long. The parallelization is maybe not the most interesting part of this. Like the most interesting part is the foundational algorithms. But because this is HPC, we can talk